Welcome to Physics Can Be Fun with me, Stephen Thomas. Today we're looking at the law of conservation of momentum, which states the total momentum of an isolated system remains constant or is conserved. Let's take as an example this balloon. If I let it go, watch what happens. So, there is our balloon, and air is blowing out of it, and our balloon experiences a force which moves it. But what is an isolated system? Well, our balloon started with no momentum. It gained momentum to, let's say, the left. So we seem to find that suddenly the balloon has got momentum. But in our law it says that the total momentum of an isolated system, the momentum remains the same or is constant before and after. So our isolated system has to include something with momentum to our right, and that is the air. So here is a force, here is a force. Here is a momentum to the left, here is a momentum to the right. And our law states that, well, Newton 3 states that the force left is equal to the force right, but our law of conservation of momentum states that in an isolated system, which includes balloon and air, the momentum to the left is equal to the momentum to the right. Let's give you another example. Here we have a radio-controlled plane. Here are its little propellers on either wing. Let's switch it on, and the plane gains momentum and it starts to move left. So, if this is our plane, and here's its propellers, the plane gains momentum to the left. So there must be something gaining momentum to the right to conserve momentum. And that is the plane is pushing back air. So here is a force that is pushing the plane to the left, but there must be an equal and opposite force from, if we add up these two lots of air being blown back from the propellers, they add up to this force. So the force left is equal to the force right. And the momentum left is equal to, combined, the momentum right. So our isolated system would have to include the plane and the air. If we just looked at the plane alone, the momentum would seem to be increasing to the left only. But if we consider all the changes in momentum, the momentum to the left is balanced by the momentum to the right. Let's give you a third example. Let's suppose we have a car, a little radio-controlled car. Now let's get the car to move left. There, the car moves left. It appears to be gaining momentum to the left. But watch what happens if I take two round pencils and place a piece of cardboard on these two pencils, which is going to reduce the friction. Now watch what happens. I'm going to leave this piece of chalk here where the cardboard starts, and let's watch what happens when I press to make the car go left. Did you see what happened to the piece of cardboard? It went right. So if we were to draw our system, we would have a little car. Here's our racing car, and our racing car appears to be forced left. So here's our force, and it also appears to gain momentum left. But there's something that must also gain momentum right to keep the momentum conserved. And in our case, it was the piece of cardboard that gained an equal force and an equal momentum to the right. So our isolated system has to include the car and the cardboard. But what if we don't have a piece of cardboard? What if we just have the car riding on the earth? Well, then the earth gains the momentum. So it's either a piece of cardboard or the earth that is going to have to gain momentum. We could perform many more experiments like this. We could take a golf ball. Let's look at this case of a golf ball. And we're going to throw it along this track and it hits a little wall. Watch what happens. So our golf ball appears to be going right. Here's our golf ball. It hits a wall and then it bounces back. How can momentum be conserved? If the momentum started off to the right and the momentum ends off to the left, it appears that momentum is not conserved. But if we consider that in the change of momentum, where the momentum of the ball went left, something had to go right. And that is, if there was a force that forced the ball to the left when it hit the wall, there was also a force on the wall to the right. And if there was a momentum of the ball to the left, there was also a momentum on the wall and on the earth to the right. So our isolated system has to include the ball and the wall. We cannot just look at the ball alone because then it is not an isolated system. So the law of conservation of momentum tells us that in an isolated system, there is no net force, in fact. The force left equals the force right. The momentum left equals the momentum right. That is an isolated system. If we just had to look at the balloon, or the plane, or the car, or the ball alone, it would appear that the momentum is changing. But if we look at everything, then if we look at the two objects generally that are experiencing a change of momentum, then their momenta and their forces are equal, balance out, cancel each other out. And that is the basics of the law of conservation of momentum.